Hello everyone, welcome to Mechanical Behavior of Materials Part 2 course. So as I have already mentioned in the introductory video that in the last semester we offered a course on Mechanical Behavior of Materials Part 1 where we discussed about starting from elasticity and then to plasticity, right? And in the plasticity, we talked about different type of testings like tensile testing, hardness testing, impact testing, etc. And then we also introduced the concept of strengthening mechanisms, where we discussed about solid solution strengthening, precipitation strengthening, then grain boundary strengthening, etc. Okay. So that was our first part of mechanical behavior of materials. In the second part, which the first lecture starts today, here we will talk about on fracture, fatigue, and tree phenomena in different kind of materials, including polymers and ceramics and composites also. Okay. So today we are going to start with the first lecture on mechanical behavior of materials, part 2. And this lecture will be we will discuss about the calculation of theoretical strength, and then we'll talk about Griffith criteria and Mills criteria in the fracture mechanics. Okay, so let's start discussion about calculation of theoretical strength. Okay, so we need to calculate the theoretical strength. And why I'm doing this? Because I want to introduce you the concept of defect, which will lead to the concept of fracture mechanics. Okay. So to do that, let me draw a schematic of atoms. So you have atoms like this. So all these are atoms and solid spheres like. And in the last semester, we have discussed about the calculation of shear strength. So it is similar to like that. So we are introducing here some springs. Okay. So atoms are connected through springs. That is what we are assuming. So all these are the springs here. Okay, so all these blue lines, these are the springs. Okay. Now, if I want to break this material, what I am supposed to do, right? I have to break this whole bond, this. I have to break this complete bond, isn't it? So if I want to break this material, suppose I am applying a tensile stress, tensile loading, this material is under tensile loading, this whole bonds in this particular plane needs to be broken, right? And then these two parts will be separated. So that is the stress what we require, and that is what we are going to calculate, and that will be termed as theoretical strength. Okay. So basically we are going to have two parts from here. And the stress required to do that, to separate these two parts along this particular plane will be called as theoretical strength, and that is what we are going to calculate. Okay. So what we are using here is called ball and spring model. Many of you might be knowing about this. Okay. So you know about springs, right? So if you apply a force then there will be some displacement, and we know the formula corresponding to that force. What is the force requirement, right? The similar concept we apply when we talk about atomic structure, and that's why we have introduced here the spring, that these atoms are attached with the spring so that we can apply this ball and spring model. So you have, say, again two atoms and they are connected with a spring. Okay. Now, if I have a spring, what is the formula for the force? So I'm talking about the magnitude. So force will be given as, and I'm applying a force in these dimensions. So F will be given as Kx, right? Where x is the displacement from the equilibrium condition. So if this condition was the equilibrium condition, x will be the displacement from the equilibrium condition. So this is for your spring, right? And this K, we know this is called as spring constant. Okay, so this everybody knows, right? Now let's apply the same thing in the atomic structure. So there we can write F equal to S into R. Now R is the displacement from the equilibrium distance, right? So if there is no force, the atomic structure is in equilibrium condition, right? The minimum energy condition. I will show you the schematic, what I mean about the minimum energy condition. So from that, what the displacement, right? Whatever we are having. So that is R, and F is the stiffness or bond stiffness. You will see in many books, says bond stiffness. Okay, and R, I have already mentioned, it is the displacement from the equilibrium under the application of force. Okay. So this is the similarity with the spring of this atomic structure. Let me just show you a schematic very quickly about the energy versus R. So in the y-axis you have energy, and in the x-axis you have distance, right? So what I am talking about here is, so you have two atoms and this distance is R naught. Okay. So this is in equilibrium condition. That means the energy has to be minimum, and that means this distance here is your R naught. So there is no force, okay, and energy is minimum. Okay, and your atom is, say, here. So I'm going to come back to this particular diagram. How did we uh, uh, know the nature of this diagram? That is the next step we are going to do. Okay, so why I am introducing this concept is because of this R naught and the displacement I mentioned just before, right? The R. Okay, so the similarity between the spring and the atomic structure. Okay. Now let's calculate the interatomic potential. So calculation of interatomic potential. So the potential between atoms can be given as U equal to minus A R to the power M plus B R to the power N, right? And in general, N is greater than M. The first term here is the attractive energy. And the second here is repulsive energy. Okay. So let me denote this attractive energy as EA and repulsive energy as ER. So the total energy can be given as U equal to EA plus ER. Okay. Now see the sign also, right? One is negative, one is positive. So attractive energy is negative and repulsive energy is positive. Okay. So what we are going to do? We are going to now plot this total energy with respect to R distance. And what you are going to get is this particular graph on the top here. Okay. So in the y-axis, you have energy. X-axis is R. Okay. Now, the total energy I have already told it's ER plus EA. Okay. And we also know N is greater than M. That means repulsive energy is decreasing much faster than EA. Okay. So repulsive energy is decreasing much faster than EA. Okay. So now let us plot both ER and EA together. Let me change the color now. So ER will be given as something like this. Okay. And EA can be given as something like this. Okay. So this particular term on the top is your ER and here this one is your EA, right? Remember attractive energy in the last slide I showed you, it is negative, okay? And the result repulsive energy is positive. So these two curves look like this. Now the total energy is what? ER plus EA. So we can just sum these two, right? So your resultant curve will be this. Okay, something like that, right? So this purple color, this becomes your U. And this is U equal to ER plus EA, right? And this is the curve, if you remember, just now I showed you this particular curve, the purple one. Okay? So this is energy versus R plot. Now you can see it is decreasing, it goes to minimum and then it increases, isn't it? And this particular distance here is your R naught, which is the minimum energy state, that is the structure is in equilibrium condition. Okay. Now, what is our overall aim? We have to calculate the theoretical strength. That means we have to also know the force, isn't it? Now, and we also know how can we convert energy to force, right? What is the what do we need to do? We need to just take the derivative, isn't it? So what we can do? Force is du by dr. So we have to take the derivative of energy with respect to R, and the resultant term, whatever we are getting, is the force between the atoms. And if we can know that, we can calculate what is the stress relevant stress, right? Respective stress, and from that we can calculate what is the theoretical strength, right? That is our aim. So let's take the derivative. So if I do that, so I'm taking the derivative of this particular term. Okay, so you have now force on the y-axis. This remains R. So force versus R. Okay. You also know that this particular line R naught should correspond to 0. So this point is fixed, right? Because its equilibrium condition force is 0. So we know that this point is 0 here, this particular point, which will correspond to R naught. That much we know not till now. So if I just take the derivative, we can have two lines. So one will be like this. Okay. And another one be like this. Okay. So now this, the top one will correspond to attractive force. And the bottom one is your repulsive force. Fire and F. And the resultant is going to be this. Something like that. So the purple one is your resultant force between the two atoms. Okay. And this particular point here, this will correspond to R naught, right? And that means force is equal to 0. That means du by dr. So force is equal to 0, right? That means du by dr is equal to 0. So derivative is 0. That means it's the minimum, right? So this particular points here corresponds to the minimum energy. So your whole system is in equilibrium. There is no force, right? So now you know the resultant force. Okay. So one quick concept I will tell now. So you now know the your resultant force is something like this. Okay. So say this is your one curve. So force and R. So you have now say two material. One is the curve I have just shown, and another one is something like this. Right? So if you see the slope of these two curves, in one case your slope is higher, right? This one. This one. And in another one, so let me mark it here so that you can understand it better. So this is number 1 and this is number 2. Right? So if you see the slope of 1 is higher than slope of curve 2. What does it mean? It means the stiffness of curve 1 is higher than the stiffness of curve 2. That means in the curve 1, the bonds are strongly bonded. Right? So if I have two materials, if we can calculate the force versus R curve, we can figure out which one is strongly bonded. Right? So in this case, curve 1 is strongly bonded. Right? You know already, right? Stiffness is dF by dr. So you have to take the slope. So higher the slope, higher the stiffness is. That means the curve is going to be, or the material is going to be strongly bonded. Okay? There is a strong force between two atoms. Right? So one quick concept from the resultant force between two atoms. Okay? Now let's come to the stress. So if you know the force, we can know the stress also, right? So stress can be given as something like this, right? So now I'm talking about only the positive part because I will be mostly dealing with the tensile stresses or tensile loading, right? So we are just dealing with the positive part of it. Okay? So here you have now stress in the y-axis and s-axis is your R. Okay. Now here you can see this is the maximum one. So this becomes your theoretical strength and this is what we want to calculate, right? So sigma TH is your theoretical strength. Right. So the maximum stress this material can bear is sigma TH, and you can also see that from the curve here. At this particular point, we correspond to the maximum stress which this material can bear. So we have to calculate this. This one we already know. This is your R naught. We have just discussed this. So let's simplify it. We can write this whole stress as sigma equal to sigma TH sine 2 pi R by lambda. Now what is lambda? Let me change the color quickly. So this is your lambda by 2. So what we are doing, we are assuming this whole curve as a sinusoidal curve for approximation, right? We have to calculate the approximate value of sigma TH. So we are just, so this particular length. So this becomes your lambda by 2, half of the amplitude of the sinusoidal curve. Okay, so we are approximating this particular curve as a sinusoidal curve. So this here R is lambda by 2 and then here R is 0. So now sinusoidal curve, right? So this particular sinusoidal curve can be written as sigma equal to sigma TS sine of 2 pi R by lambda, where I have shown what is R and lambda is also I have shown here. That is the amplitude of this particular sinusoidal curve, right? Now since 2 pi R by lambda, we are talking about atomic distances, right? These are very, very small. So we can again approximate the above equation as sigma equal to sigma TH 2 pi R by lambda, right? So this particular equation can be written like this. And again, approximations. So let me mark it as equation number 1. Remember that this is our equation number 1. Now the strain can be calculated as what? Delta L by L naught. And that you know now from the previous course on part 1 that if you have a tensile loading, we say, and there is an increment in the length by delta L. So we say delta L by L naught, where L naught was the original length, right? So let's apply the same concept here. So what was the original distance between the two atoms? That is R naught, right? Okay. And what is the increment in the distance? That is R. That is a change in the distance between the two atoms, right? So strain can be written as R by R naught. Okay. So R naught was the initial distance, and then there is an increment in distance by say R, right? So the strain is R by R naught. Okay. Now what is Young's modulus? That is given as E equal to sigma R by R naught. Okay, so the stress by strain, stress is sigma here, strain is R by R naught, right? So for small distance, we are having the validity of Hooke's law. Remember, we are just talking about the small increment, right? And there, Hooke's law is going to be valid. So this is now your equation number 2. Now let's combine equation number 1 and equation number 2. So we can write ER by R naught equal to sigma TH 2 pi R by lambda. Okay, so what I am doing, I am replacing this sigma by sigma TH 2 pi R by lambda. So you are going to get this particular equation. Okay, or we can write this whole equation as sigma TH. The R will get cancelled out, right? Okay, so we can write E lambda by 2 pi R naught. So we have calculated the theoretical strength of a given material, right? Which will depend upon the modulus, lambda, R naught. Okay, these are the three dependent variables. Let me mark this as equation number 3. Now, in general, this lambda, okay, this amplitude of the sinusoidal curve, what we have assumed. Again, remember, these are all approximations we have made, some approximations, right? So this lambda is in order of the R naught. Again, one approximation we are adding now. So in general, lambda is in order of R naught. So equation number 3, that was sigma TH equal to E lambda by 2 pi R naught. This equation will be now sigma TH. So I am replacing lambda by R naught, right? Again, all these are approximations. So let me put this sign here. Huh? Okay. So E by 2 pi. So theoretical strength is E by 2 pi. In some of the bores, you will see that it will come out to be E by 10, E by pi, right? But remember, all these are in the same range, approximately same range. All these will be in the GPA. You will see eventually, right? So this is the theoretical strength you have calculated, E by 2 pi of a given material. So this is method number 1, where we have used the sinusoidal curve and the concept of strain, modulus, etc., and came up with the theoretical strength calculation. Now let's use the concept of energy and calculate again what could be the theoretical strength. So that is method number 2. And we are using surface energy consideration here. Okay, so let's calculate the fracture work per unit area. And this can be given as integration of 0 to lambda by 2 sigma dr. Okay, so you remember the sinusoidal curve, right? So what we are doing, we are calculating the fracture work per unit area, right? You know work, that is F into S. So when we are talking about per unit area, it will be sigma into X, right? That means sigma into dr. And we are integrating that particular sinusoidal curve to calculate what is the overall work done, right, to fracture. We can write this as 0 lambda by 2. And what is sigma? Sigma is sigma th sine of 2 pi r by lambda dr. Right? So we have to integrate this sine function. And what is the integration? In terms of cos, right? So we can write this whole equation now as this, and then minus cos of 0 plus cos of 2 pi by lambda into lambda by 2. So the integration will come out to be like this. And if you solve, it will be sigma th lambda by pi. Okay. So this is what is the fracture work per unit area. Okay. Now realize this, that whenever we are fracturing or whenever we are separating two solid materials, we are going to create some surfaces, right? So the work we are doing in terms of stress, right? We are creating two new surfaces, and these two new surfaces are going to be associated with their surface energies, right? So we can equate this fracture work per unit area to the surface area of these two new surfaces, right? Because you have generated that using the energy, right? Energy you are supplying in terms of the stress. Okay, so let's do that. So we are equating now this to the surface energy terms. So this should be equal to surface energy per unit area. So we can write the equation as sigma th lambda by pi equal to 2 gamma, right? And what is this gamma? This gamma here is surface energy per unit area. Okay, and why we have added 2? Because we are creating two new surfaces, right? So whenever we are fracturing, we are generating two new surfaces. So multiply it by 2. So we can write this as now sigma th equal to 2 gamma pi by lambda. So this is the equation we have got. Okay. Now if you remember the equation 3 before, let me write down. Equation 3 was sigma th equal to E lambda by 2 pi r naught. This was our equation number 3. So let's use this here. Let us replace lambda in equation 3 by in and then put it here. Okay. So use this one and then place it here. The value of lambda. So this will be sigma th equal to 2 pi gamma, and then lambda is, so maybe 2 pi sorry, sigma th 2 pi r naught and then E on the top, right? So 2 pi will cancel out. So it will be sigma th equal to root over E by r naught then gamma. So we have got another term related to the theoretical strength, but this is based on the energy consideration. Okay, so what you see here is E R naught. R naught, now you know that is equilibrium distance between the two atoms, no forces there. And gamma is the surface energy of that particular material. Okay, so we have now got two equations. One we derived before and one just now with respect to the surface energy. Okay. So now let's compare these two and then realize the value, right? The relative value of sigma th, and then you will see why there is a discrepancy. What we have observed in reality, well, when we do some experiment in the lab and the theoretical strength values. So let's see some examples. So say you have copper, nickel, then NaCl, different material, okay, including ceramics, silicon. Okay, so let's five different materials, and then we have sigma th E by 2 pi we calculated, and the second one is sigma th. This is based on the energy, so root over gamma E by r naught. And the unit, now this is important, the unit here is GPa, the unit here is also GPa, right? Now let's see the value. If we calculate all these values, this will be and all 19 approximated values, right? 35, then 5.8, 49, 26. And this will be 24.8, 37.2, 6.3, 40.8, 28.5. Okay. So now you have the two values. There will be obviously some differences, right? Because all these are approximations, and then we have used different criteria to reach to this particular theoretical strength values. But one thing is very common here, that all these values are in GPa, right? 19 GPa, 5 GPa, 49 GPa, etc. And what do we observe when we do the experiment? Let's say copper. If you do the experiment, do some tensile testing, what is the strength you are going to get? It's in MPa, right? But here you see you are getting a range of say 19 to 25 GPa. So there is a dramatic difference between what we have calculated just now and what we observed in the material reality, the practical applications, right? Practical calculations, right? And that's when you see the discrepancy, right? And that is happening because of two reasons. So the first is, so you see a discrepancy, right? So the first is, this one have been discussed in our course, the previous course, that is because of dislocations, presence of dislocations. Right? And we have discussed a lot about concept of dislocations, their interactions, etc., including in the strengthening mechanisms, right? So presence of dislocation, and this led to the concept of plastic deformation or slip, right? Now, second, there could be presence of some defects. Okay, so other defects. Remember, dislocation is one type of defect. Now, other defects we are talking about. Excuse me. Cracks, porosity, etc. Okay. So these are the two reasons because of which we are getting a discrepancy between the observed values and the calculated value based on this table, right? And one you already know in plastic deformation, and the second one, which is related to cracks, etc. This led to the genesis of fracture mechanics. Okay, so you already know what dislocation did to the material, because of it the strain went down. Now in these lectures, we are going to study what these cracks and porosities are going to do in the material, so that the observed values are in MPa, but the theoretical values are in GPa, right? And that is the genesis of fracture mechanics. So what is actually a fracture mechanics? So you see some definitions from the books. So it evaluates the behavior of crack-like defects in structures and their effects. Okay. So if you have defects in the structure, what is its behavior and what is the effect of the presence of these defects, right? That is point number one. And the most important is that it provides you a quantitative treatment of fracture. Right? And you will see how we are going to use fracture mechanics to quantify it. There's some quantification. I will give you some formula, etc. And we are going to utilize this formula in assignments also eventually. Okay. So what are the uses of the fracture mechanics? Again, remember you have already presence of cracks, and we are evaluating the behavior of these cracks, right? And their effects. That is point number one, right? So you have a structure and there is a crack. So the first point is, what is the critical size you can have in that particular structure if you already know what is the load requirement. Okay, so that is point number one. What size of crack can be tolerated at the expected service load. Okay, that means what is the critical crack size. Okay, so you already have a structure. Now you know, say you have to apply say P load or something, right? You already know that load. So what could be the critical crack length size or crack length, above which your material is going to fail? That is point number one. Now vice versa, right? If you know the crack length say you did NDT and you already know what is the crack length in this particular say plate, right? So what could be the maximum applied stress you can have so that your material doesn't fracture? That is point number 2. What is the maximum allowable stress based on the size of flaw? Crack, right? Flaw here is your crack. That is point 2. Now point 3, you already have a crack. Say the length was L naught or A naught, because we will be using now A for crack length, right? A naught. After some time, crack length became A2. So you can calculate what is the time requirement from going from crack length of A naught to A1 or A1 to A2, okay, and so on. So that is point number 3. How long will it take for a crack to grow from its initial size to some size, other size, or critical size? But you can calculate the intermediate size also. Okay? We are talking about now till fracture, so we are using critical size. Now the last point, if you know the crack growth rate, how long? See, I know if A1 and A2, I know also what is the crack growth rate, right? And depending upon the nature of the growing crack, you can know what is the timing of inspection, right? If it is very, very fast, right, then you need to inspect your material much frequently, right? That is point number 4. How often should structure be inspected? Okay, and we are going to use this eventually. At some point of time, you are going to use this concept of in uh, in quantitative analysis. Okay, so the first experiment, who used this in the qualitative way was Leonardo da Vinci, and what he did, he took different length of wires, okay, and then loaded it and then calculated the fracture strength. And what he observed, if you increase the length of the wire, your fracture strength is decreasing. Right? Now imagine, one can always say, right, if you have a crack length or a length of the wire is very small and another length is very, very big, the detecting the flaw, finding the flaw in the larger length is going to be higher, right? And that is what he proposed, that qualitatively that the flaw size can affect the strength of material, right? So increasing the length of the wire, right, we are assuming that there could be more number of flaws, right? A critical size of the flaw will also be higher there, right? So that was the first experiment what Leonardo da Vinci did, and he observed that the strength of the wire is decreasing with increasing the length of the wire. Okay, so qualitatively, he stated that the flaw size can have an effect on the strength of material. But that was qualitative, but very nice experiment, very, very nice experiment. Okay? So now we will talk about the quantitative analysis. So we are going to introduce the Griffith and English criteria now. So the fracture mechanics approach to design. Okay. So we are having now two approach. One is energy based and another one is stress based. Okay, so stress based is your English criteria and energy is your Griffith. Okay, and in the next lecture, we will start talking about the stress-based approach, the English, and then in the subsequent class, we are going to talk about the Griffith criteria also. So here, English suggested that there should be sufficient stress concentration. Now I've introduced another term, stress concentration, which we are going to discuss next. Should exist at the critical. Okay, so English proposed that if you have a crack, suppose I have a crack, here at the crack tip, you should have sufficient amount of stress for fracture, right? And there is a concept of stress concentration, which we are going to discuss. And the Griffith here talked about the energy approach, so you should have favorable energy. Should be energetically favorable. Okay? Okay. So we have two criteria, energy and stress. And in the next class, we are going to start talking about the stress-based approach, where we are going to introduce the concept of stress concentration and some formula to calculate what could be the stress at the critical. Okay. Thank you.